Good morning, everyone. Mr. Harper here. And we need to continue our discussion on radiation. And as we do, I want to start with this slide as a review. Remember that radiation is electromagnetic waves, which are light waves. They travel in waves, as you can see here. And there are different kinds of electromagnetic waves in the electromagnetic spectrum, the range of all kinds of electromagnetic waves that range from radio waves to microwaves to infrared waves to visible light, to ultraviolet rays, to X-rays, to gamma waves. And as you move left to right, you notice that the waves, even though they have the same amplitude in this example, the same height, the waves are getting shorter and shorter and shorter. The wavelength is getting shorter, and as that wavelength gets shorter, the waves carry more and more energy because they are going to hit more and more and more frequently. So radio waves, low energy, all the way up to gamma waves, the highest energy, and X-rays here with pretty high energy. Everything below X-ray waves is called soft radiation. It has weak penetrating power. It hits your body and really your skin just about stops it. Ultraviolet rays can cause a little bit of skin damage at a very short, narrow level. Can't go very deep into your skin, cause some sunburns. But everything above X-rays and gamma waves, those are hard radiation. They can go into your body, pass right through it, as a matter of fact. So let's talk about why X-ray waves. We talked that you can't sense them, you can't see, hear, smell, taste, touch them, anything like that. But they can cause damage to your body. Well, why is that? And that's what I want to discuss today, what's going on. And as you can see here, I have an atom on the screen. I want to remind you of the atomic structure. Atom, smallest unit of element, the parts of the atom. Protons, here in the center, make these little orange balls. They're charged positively, and they are in the nucleus. Also in the nucleus, these little teal-colored balls are neutrons. They are neutral. They don't have a positive or a negative charge, and they're both found in the nucleus. Circling around the outside of that nucleus in orbitals or shells are electrons. Electrons are much, much smaller particles compared to the protons and neutrons, even though they're not shown as such in this picture. And they are charged negative. So remember those basic parts of an atom. So what does this have to do with X-rays? So first we need to talk a little bit more about an atom. A stable atom has equal numbers of protons and electrons, and it's neutral as a result because each charge cancels out the other. For example, hydrogen has one electron charged negative, it has one proton charged positive. You put those negative and positive charges together, they cancel each other out because they're equal, and the atom is neither positive nor negative. That's a stable atom. Now, atoms frequently become ions by losing electrons, and the process is called ionization. This is a natural process, happens all the time. It's the way that atoms chemically interact with one another. So atoms that have either lost or gained an electron are called ions. And there's two kinds. There's a cation that's charged positive. There's an anion that's charged negative. So if you have, for example, in this example, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons. This atom is charged negative. It started out, it only had 7 electrons, and it has 7 protons here in the nucleus. But it's gained an electron from another atom. So now it has 7 protons and 8 electrons. It is negative. We call it an anion. Now this cation, it would have the opposite of that. It would have 7 protons but only 6 electrons. And because of that, it's going to be charged negative. So atoms can become positive or negative by losing or gaining electrons. And we call those atoms ions. Cations positive, anions negative. Now, what's that got to do with radiation? Well, imagine that this is an X-ray wave of radiation. And it comes and it's bombarding your body, and your body's made of atoms, of course. That wave has enough energy to cause an atom to unnaturally lose an electron. Here comes the wave with all its energy. It hits an electron, it knocks it away from the atom. So now the atom has become a cation because it had 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons, But this electron is lost. Not only has 8, but it has 9 protons here in the nucleus. So it has become a cation. And it's not naturally become a cation. It's not a normal mode of operation for our bodies. And because of that, it can cause problems in our bodies. So the process of removing an electron from an atom, that's ionization, and that process requires energy. Normal energy in your body, that's not a problem of atoms becoming ions. But an abnormal amount of energy, such as from electromagnetic radiation, like X-rays, can cause more atoms to ionize than what our bodies are normally used to, are able to handle, and could cause problems. So, this radiation, energy sufficient to cause electrons to dislodge or leave the atom, could disrupt cellular metabolism. Remember, metabolism is how the cells are using energy, and it could cause that cell to have problems. It could damage the cell, it could cause the cell to die. Now, if that happens to one cell in your body, that's no big deal. But if it happens to hundreds of thousands of cells, it could cause problems for the organism. And understand this too. Radiation's effect in your body is cumulative, which means it builds up over time. Radiation isn't something that you're necessarily going to be exposed to and immediately have a problem. Sometimes, many times, the problem builds up slowly over decades. And so you might be exposed to radiation over, say, a period of 10 years in your 20s, but not develop a problem from that until you're in your 60s. This period of time, this lag, is called the latent period. The latent period is the period of time from when you're exposed to the period when symptoms actually show up. You know, if you're in an accident and you break your leg, latent period, there is none. It's like seconds. But if you get cancer from smoking, that might take years and years and years to develop, and radiation exposure is like that, the latent period. And radiation's effect is cumulative. It builds up in your body's tissues over your lifetime. And exposure can be acute, or it can be what is called chronic. Acute will be a very large dose of radiation in a short period of time, and effects show up immediately. I mean, a huge dose. Or it can be chronic, small doses over a long, long, long period of time. And we'll stop there. So, we've talked about how radiation can cause atoms in your body to ionize, to lose or gain electrons, and that could become a problem because it could disrupt cellular metabolism. We also talked about how radiation has a latent period. Usually, exposures are usually chronic, small doses over a longer period of time, and the results of that occur much, much later, and the period of time between exposure and symptoms showing up is called the latent period. We'll talk more next time.